Okay, here's a video giving a time division multiplexing example problem. And in this problem, we have 6 input sources, 2 with a data rate of 1.25 megabits per second, and 1 with a data rate of 0.5 megabits per second, and 1 with a data rate of 0.25 megabits per second. Let's see, 2 plus 1 plus 1 is 4 input sources. Let's work with 4 input sources. And so we've got 1.25. Let's call this R1. We have 4 of these input sources. R2 is 1.25. R3 is 0.5. Here's number 3 coming in. Here's number 4 coming in. R4 is 0.25 coming into the mux, the multiplexer. Okay, so now we've got to figure out how we're going to make this frame. Well, the lowest data rate is 0.25, and so that one's got the slowest bit arrival time. And if we're going at twice that speed, then 2 bits from 3 arrive whenever a bit from 4. Let's call these A, B, C, and D. So when in the time it takes for 1 bit to arrive from source D, 2 bits arrive from source C. Similarly, 5 bits arrive from source B, and 5 bits arrive from source A, because source A and B are 5 times faster than source D. And so, in a certain amount of time, we're going to get all these bits arriving. And if we do bitwise, let's see, design a frame structure appropriate to handle these data input rates, create the smallest frame possible, and do not include a framing bit. What is the size of the output frame? Well, let's do bitwise interleaving and create our output frame something like this. A, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2 C's and 1 D. Okay, so this is going to be our frame structure. Okay, no framing bit. And so the size of this frame, number of bits in a frame, is 5 plus 5 plus 2 plus 1, which is 13 bits. Okay, the output frame rate. Now, we're going to use the same equation that we did before. The output frame rate is the rate of one of the inputs divided by the number of bits in the frame from that input. But now we've got multiple different input speeds, and so that complicates things. But what we can do then is we can say that for any one of these inputs, R1 over N1, R2 over N2, this has to hold for all R4 over N4. This has to hold for all 4 of the input sources. And we can double check that we're doing things right. N1 is A, the number of A's. N1 is the number of bits from source 1 that we get in a certain amount of time in the frame. N1 is 5, N2 is 5, N3 is 2, and N4 is 1. So let's go ahead and divide those rates by those numbers and make sure they're all equal. R1 over N1 is 1.25 over 5. R2, 1.25 also. N2 is also 5. R3 is 0.5. And N3 is 2. And last but not least, source number 4, 0.25 is its rate, and it only gets 1 bit in the frame. And indeed, all 4 of these equal 0.25. And so this is the frame rate, and if this is 1.25 megabits per second, then this is going to be 0.25 megabits per second. Okay? So this is one way of checking that you've got the number of bits in the frame correct. Is if you divide the data rate by the number of bits, it should equal a constant for all sources. Okay, that ensures you're doing it right. Calculate the output frame period. Well, if this is the frame rate, then the frame period is 1 over the frame rate. 1 over 0.25 times 10 to the 6th, which is 4e to the minus 6, or 4 microseconds. Finally, the output data rate, or our out, or our tot, what do I call it here? Our total. Well, because there are no framing bits, it's the sum of the data rates. It's R1 plus R2 plus R3 plus R4. Okay? And this is 1.25 plus 1.25 plus 0.5 plus 0.25, which is 3.25 megabits per second for the data rate. Okay? So I hope that this example helps you in creating frame designs and doing the calculations for TDM multiplexing, where we have different speed inputs. Hope this helps.